Okay, well, thank you very much for your patience. Sorry for this mishap. Thank you, Giulio, for taking over impromptu. Thank you for the organizer for inviting me. You'll see at the end of the day that this was all a plot so that I could build on the nice introduction by Giulio, because he covered a lot of the material that I will need. So this is going to be joint work with Nick Boffey, who was a postdoc at the Courant Institute and is now a faculty at CMU. Okay, and the reason why I need the background from Giulio is because I'm going to use generative AI and diffusion in particular, or tool from them, to analyze problem in active matter. So I don't think I need an introduction for this audience of what active matter is. There was the talk by Mike Hagen. The system that I'm going to be focusing on are simpler than the one that he showed because they are synthetic. One is active OU process that undergo MIPS, and the other one is flocking in VSHEC. So both these systems have a dynamics that is not in detail balanced. There is some active force, and as a result, they do things that would not be possible by, without the activity. I'll go into detail of that later, but this one is essentially particles that repel, but they have an active force that forces them to swim in a given direction, and this direction is persistent. And so what can happen, in a nutshell, is that they can bang into one another, and that can create, if there's more than two, that creates a big traffic jam, like this. Okay. This is a variant of VSHEC model, which is also a fairly well-known model, where this is essentially Langevin equation, except that the velocity field tends to align itself. So there is something that aligns the velocity field of particles that are in a certain radius of one another, and so they can create these flux. Okay, and the question that I would like to ask is actually fairly simple. Is a bit of a delay, but so these systems are in a non-equilibrium statistical steady state, and I'd like to quantify how far are they actually from equilibrium. Okay, and there's a simple way, maybe a layman way, to actually ask this question, which is maybe the one that I focus on, is that it's about breakup of time reversal symmetry. I want to ask you whether these movies are played forward or backward. Okay. For this one, this is all you see. This one you would play it backward, but you would put the arrow on the other side. So if these were equilibrium system that satisfy detailed balance and that are in an equilibrium statistical steady state, there would be no statistical test that allows you to tell whether I'm actually playing the movie forward or backward in reverse. But since these are active systems, it could be that you can tell. It could be that the activity creates some non-equilibrium effect that are detectable statistically. That's the question that I would like to ask. Okay, and it's a I'm not the only one asking this. Of course, it's a very well-known question in the field. Okay, so the way we're going to be discussing this is first I'll give you a few slides that are general theory, very simple in a way, where we're going to assume that there's a microscopic dynamics, which is the diffusion. So there's a stochastic system, and here R denotes all the degrees of freedom that you have in the system. So the position and or active forces of all the particles in the system. So for MIPS, for example, particle moving 2D, and they have an active force. So that's 4 times n, which is the number of particles that you saw. That would be the dimensionality of R. And for VSHEC, similarly. And then the equation contains a drift term, which is like what is the force that is deterministic. But I will also assume that there is some noise, which is not of thermal nature. There is some randomness in the system. Later in the talk, we're going to get rid of it. Okay, so I mean, this is really undergraduate stuff in a way. You know that you can describe the statistics of this dynamics by looking at the probability density function of the particle position, this degree of freedom, and it satisfies the Fokker-Planck equation that they have written here. Okay, and this is a conservation law where there is a current that appears, this guy, which is written. And the way you can characterize a non-equilibrium statistical steady state and distinguish it from an equilibrium statistical steady state is that if you reach a stationary state, which means that the probability density function stops moving, the particle of course still moves, but on average they don't. You can ask yourself whether the current is equal to 0 or not. If the current is equal to 0, it's an equilibrium statistical steady state. If it's not, but its divergence is equal to 0, it's a non-equilibrium statistical steady state. Okay, and this is all well known, of course. You can, based on the current, define something which is called the current velocity, which is just the current divided by the PDF, and it has this specific form. And this form will be very important in a minute. There's just a little identity here that has been used, that the grad of rho divided by rho is the same as the grad of log rho. Okay. Now, this velocity field appears, plays a very important role because it also, there's a more direct way that this is related to non-equilibrium statistical steady state, namely that you can, by doing simple manipulation on the Fokker-Planck or with other tools, you can actually write down an equation for the time reverse dynamics, and it involves this V, which is again defined this way. So what is this dynamics? It's essentially, so if you were to generate a movie simulating this equation, and then you had to play it in reverse, there's another way to do that, which is that you could directly generate the time reverse movie by playing this equation, by simulating this equation. And you see that they differ by this drift term, which was written there. And well, clearly, if V is equal to 0, they are the same. And that means that the current is equal to 0. And if V is not equal to 0, they are different. So the two dynamics are different. The time reverse is different dynamics than the original. Okay. And this is well known from Nelson's book, Anderson. There's even mathematical theorem about that before. Okay. So this is really, this is like playing the movie in reverse, not by generating it forward and playing it, but just generating directly like that. And this is what I've just said. And so, in principle, if you want to understand or quantify non-equilibrium nature of the dynamics, you could try to calculate this V. The difficulty, and that we're going to get in a minute, is of course that this is in a way a monster because it depends on the grain of the log of the probability density function that you don't know. It's a non-equilibrium statistical steady state. And this is a very high dimensional object. This velocity field is a velocity field, it's a vector field that acts on all the degrees of freedom of the system. Okay? So the main part of the talk will be to try to explain how you can use generative AI to calculate or estimate this. But just to fix idea, and before I say that, but this I will not elaborate, I can discuss that offline. This velocity field also appears in various definitions of what's called entropy production rate that you can derive using the tool of stochastic thermodynamics or by using fluctuation, these fluctuation theorems a la Crookes and Jarzynski. Okay. This they may not explain. This is essentially saying that if you look at the way, if you calculate the relative entropy of a path measured on the actual measure with respect to from the path measure of the reverse path measure, it's related to the average of this V. Okay, so that's just telling you that V is important at the level of the EPR. Oh, confirm you speak in English. That is quite insulting. Okay. Well, I'm trying to speak English for those of you who have not noticed.
Statistical physics.
Well, it's actually, it's very good for when you present AI. This is a reminder that AI is actually, okay. If we could get rid of it, though, so that we know that I'm trying to play. I need to make it here, baby. I don't want to, I mean, I don't wanna... No, don't say it. Cancel. Okay, okay. Okay, so here's an example. So just to, before we go to high dimension that explain what's going on in low dimension, and show you that the activity can actually have a role that's important. So it's a particle that is moving in a quartic web. So it has a non-elastic restraining force minus x cubed. And then it has a force that's added, which will be active, which is given by an Ocean-Hilbert process with a certain persistence time that is the inverse of this gamma, the friction coefficient. So if you were to send gamma to infinity, this active force would become non-persistent. It would have zero correlation time, in which case the noise that you have in the equation for H would just become white noise. So it would become a thermal system. And you know that if it's a thermal system, then what you would get is that you would have an equilibrium statistical steady state. And since this force is the derivative of a convex potential, which is just x to the 4, you would get just the distribution would be monomodal in the center. But because there is persistence, what can happen is that for a while, the particle is pushed either to the right or to the left, and it has a tendency to stick to the wall until the force reverses itself, which takes a little bit of time. And so if you look at the probability density function in the X G space, you see metastability, meaning that there are two blobs where there is probability mass that are away from the center, right? And this is G positive, so it's pushed this way, G negative is pushed that way. This is what you see if these are the actual trajectories, just for reference. And you can, calculate the probability current, and you see that there is a non-trivial probability current. It's not equal to 0, so it's non-equilibrium. And you can calculate the EPR, which actually is telling you in this system that there is no entropy production or consumption when the particle is away from the wall and all is happening at the wall, which is also something that is, quite intuitive. Okay, the question is again, how do we scale up these calculations that you can do them in high dimension? And this is where I can rely on the fact that Julius spoke before me, which is that, as you know, there's been an explosion in generative AI of tasks like, giving a prompt and getting a fake image that corresponds to the prompt, or doing things that are, in fact, more relevant for science, like finding what is the folded structure, where here the prompt is what is the primary structure of the protein, or doing weather forecast, where the prompt is what's some information about the weather today or yesterday, and you want to know what is happening tomorrow. All of these applications are application of diffusion or score-based diffusion, and I have the same image here as Julio, which is that the way this is done, and since Julio has explained, I don't need to really explain it to you, is you take your data and then you move them forward in time until they devolve into noise, and then you learn how to move them backward in time. And the thing that I want to point out is that in order to do this reverse dynamics, it's exactly the same equation as the one that they've written for you before, except this is non-equilibrium, but you need to learn the score. And in fact, the big advance, the breakthrough was to realize that you can actually learn this score from data. So I'll spend one slide to explain that to you because it's kind of an interesting identity, and which is so what we learning the score is essentially using machine learning, and this I will not explain to you. I'll give it in a slide in a minute, but essentially we're going to use a deep neural network as a function approximation for the score. But let me explain how this is done. Right? When you do machine learning, you always need to, this is maybe I went a little bit too fast on this. You use a deep neural network to approximate a function, and then you write down an objective for this function that needs to be tractable, meaning that you need to be able to evaluate it on data. And then you represent the function that you want to approximate by a deep neural network. It's just like a function approximation. And then you view this objective as an objective or a loss for the parameter neural network, and then you optimize it owing to the fact that you can estimate the loss empirically. Okay, let me try to explain this in practice. In particular, I'll show you what is the loss. Suppose you want to learn the score. What you can write down is this Fisher divergence as a loss, which is if you take the expectation of grad log rho h minus grad log rho squared, the minimizer of this objective function is h equal grad log rho. This, however, is an expectation of an object that you don't know, because that's what you would like to find. Okay? But then there's this little identity which come back from Vanden-Eijnden and Vincent that say, well, expand the square And then realize that this term here doesn't depend on A, so you can drop, it's a constant as far as the optimization is concerned. This one is the expectation of H square, that you can evaluate because that's the neural network that you will use. And then the probabilistic one here, you realize that grad log rho times rho, that's grad rho. You integrate by part and write it like this. And now you realize that the score is the minimizer of this objective, but this objective now you can estimate on data because it's just an expectation over. That means what? Is that you have this loss, and then you estimate it on data. You have written it as a sum over time slices, for example, of system that is evolving. And once you have done this, you go back to what I was saying before. Now you can apply the toolbox of machine learning to this, which is you can represent this guy here. So this is how you estimate the loss. You can estimate it for any parametric representation of H, and you use a parametric class that is very expressive, named the deep neural network, and you optimize this. Okay? If I had given this talk 15 years ago, people would have said this is lunacy, because trying to do parametric estimation of function in high dimension like this would never work. It turns out that, for reasons that we don't fully understand, it does work in high dimension because there is structure in the data, and there is the power of this deep neural network. And we don't really understand why, but there's empirical evidence because all the diffusion method generative models that work on diffusion are based on this. So they actually learn the score to sufficient accuracy that they can reproduce image. Okay, I want you to pause on this because it's really a remarkable fact, which is that even if we were to reproduce the data set, even if we were to memorize, it is still a remarkable fact because you would memorize the data set in a very non-trivial way, which is by learning a velocity field that gives you back images in this data set. Even that is like completely, magic in a way. It does more than that. It allows to generalize. Okay. All right, so, here's a little, what we're going to do now, and I'm not going to explain much of this, is that you have microscopic dynamics. So above is this idea that you can write down the Fokker-Planck equation. The Fokker-Planck equation, you can rewrite it as including this velocity field that is a current velocity field. And then if you had this velocity field, you could actually look at the probability flow, which is just the evolution of this on this velocity field, determine the equation, and look at the entropy production rate. And the way this is going to be done in practice is that you have particle data that is, used to optimize the score, which is essentially the one that I wrote, except that there's a few relations that you can impose on top of it to help the training. And then once you have learned the score, you can use it as an approximation to actually look at what the velocity is. Okay, and that's really for the aficionado, but this use transformers architecture, which are very well adapted for this type of problems because they are invariant, they are equivalent. They give you things that are invariant by permutation. In fact, they are more adapted for this type of problem than they are for text, because here you don't need to have the other token for the localization in the image. They are really completely invariant by permutation. Okay, so if you do this, I mean, I've completely lost track of time, but you remind me.
Yeah, don't
All
worry.
right. So if you do this, you can. So let me now go into MIPS and explain how this is done for MIPS. So the variant of MIPS that we looked at is the variant in which it's hypoelliptic, so there is no noise on this. We could have put it in the later part of the talk. I've shown you an example where there is a bit of noise there, and then there is this equation, right? And this is a simulation of that. For the right shows, so F is a repelling force, 2 body. You choose the parameter. Okay. And okay, so what you can do here is that you can carry on the program that I just explained. Namely, you can learn the score, which means that you can replace this equation by an equation in which, so this what you see here is that, of course, the velocity that you need is just this one. But in this equation, you need to replace that by the part that comes from the score. And this is essentially what you learn. And once you have done that, that means that you have access to this Vij, and you can plot it Okay, to avoid misunderstanding, I want to insist again that this is something that is done by using what we call a data point here, is one snapshot of this. Okay, there is no averaging over the particle that is there. You need many replicas, so you need to run this for a very long time. And then once you have done this and trained, this velocity field here, okay, this score here, is a complex function that depends in principle on all the position and all the forces of all the particles. Okay, it is, however, decomposable in particles, so you can actually plot what it is, and this is what I show you here. Okay, and these figures will not surprise Jack, Mike, Cesare, because they show that all of the activity is actually happening at the equivalent of the wall here, the wall of the other example, namely when at the interface between the bulk and the gas. Okay, this is the only place where V is non-zero, like if you look at it component-wise. So it's confirmed that in this system, they are out of equilibrium because V is non-zero, and this what the activity is there. Okay, and then you can, to emphasize the fact that, so this is a calculation that is done once and for all. You're training this score, and then you can actually use it to analyze simulation on a test set on the fly. So you can actually create movie of how the entropy production rate is evolving in time. And this is what you see here. If you look closely, this is going through Zoom, so there's a bit of a delay. But you see that there is entropy production rate when there are defects, that are grain boundaries that are going through the and then you can, this is, you can scale these things up, meaning that you can do transfer learning, but we use specific, so you can learn at one scale and then transfer the information that you need at other scales. And here you see really, the place where more and more you get that, that the interface becomes sharper and sharper with no entropy production here, there, and although in the gas, you see actually this, right, that there are more particles in the gas than the one that are there. These are mini clusters, so that's why there is a little bit of entropy production rate, right? And then you can also go through packing fraction to see that, as you increase, like when you're in the gas phase, essentially there is no entropy production rate, then there's this mini cluster that appears, and then you have the big clusters, and then you go into state where everything. And you can, you can do the same thing for blocking. I'll just go through that because I think, so here the system is, so if this term was not there, this would be simply, under-damped Langevin equation, where it's just Brownian motion. But here what you have is that there's a kernel that says that if two particles are sufficiently close to one another, so it's a function of the distance of the two particles, then there is a force that essentially aligns VI with the average value of the velocity field, the velocity of the particle in the neighborhood. And that's what creates this flocking. Okay, and so you can do exactly the same thing as what I did before, and you can. It's interesting that it didn't start at the beginning. Okay, you can, color the particle according to either divergence of the velocity computed or the norm of the velocity, and it takes a little bit of time to look at this movie, but what it actually says, if you look at them, is that this shows you all the particles in the flock or in the system, and what you see here is that basically the only one for which this velocity is non-zero, that have entropy production, are the ones that are either leaving or going into a flock, or when they are breakup of the flock. Okay. Otherwise, when they are in the flock, that's equilibrium in a way. When they are all separated, it's also equilibrium. It's when they interact through this active force, then there is something that's going on. And again, what these movies show is that you can actually calculate the entropy production rate on the fly, since you have no function evaluation that gives you what this velocity is, so you can calculate what is the system EPR or the total EPR on the fly, and this becomes function that are the average give you the total entropy production rate, or like, but here you have the microscopic motion, and so you can do, for example, statistics. When I am too far away from this field to really know what exactly that means, but you can plot the histogram of the entropy production rate on time slices of a trajectory and show, for example, so the system EPR needs to average to 0. This one is always positive, but you see that the way entropy is produced and consumed in this system is different. I don't know what exactly that means. We can, probably expert in the room would know better than me. Okay, how much time do you have then?
10 minutes.
10 minutes. Okay. So what I've done so far is essentially showed you that you can use these tools from generative AI almost sort of out of the box to analyze the active system when you have the equation of motion that are diffusion. Because at the end of the day, as Giulio explained, what you do in score-based diffusion modeling is manipulating precisely stochastic differential equation, learning the score to time reverse them. And that's exactly what we have done in the previous slide. It's just saying, instead of doing it to do images, you can actually do that to analyze your active system. Okay. But I want to end the talk with something which is maybe another application of generative AI, which is more direct, which is that often it is the case that you observe trajectories from experiment, for example, where you only observe a subset of degrees of freedom. What I mean by that is that maybe there exists a Markovian dynamic somewhere that would involve all the degrees of freedom, but you don't really know what it is, and you can't observe them all. Like for example, when I showed you the movie of the MIPS, and I asked you, is it played in reverse? I cheated you a little bit because I only showed you the position of the particle. But in fact, to do the calculation, I needed not only the position, but the active force, which is not shown on right? And so another question is, suppose you only have trajectories that are given to you, or snapshots of these trajectories. Can you do something that will actually also allow you to tell whether there is breakup of time reversal symmetry? And yes, there is. You can, in fact, use generative AI again, and this is with Corentin, work with Corentin is still in progress. But essentially, what you can think about taking pieces of trajectory of a certain length and declare that this is your data. It's a high-dimensional data, but so are images, right? It's all the time slice of all the particles in the system. And what you can try to do is to learn a generative model that will generate this data, that will turn noise, if you wish, into trajectories from the data that you have. Now, if you do that, and this I don't have time to explain, but I would be very happy to do so offline, if you're interested, is that what these generative models do is essentially they learn the trajectory distribution in the sense that they not only they are allowed to sample it, but they also are allowed to calculate likelihood. And that's essentially, again, because you have access to the score somewhere down the line. No, here is no longer the score explained before. It is the score that you need to learn in order to push noise into trajectory data. Okay? But if you have that, you can actually calculate the likelihood. And so if you have this, then what you could do is simply, there's many things you can do, but one thing that's simple to do is that you can learn a generative model to generate trajectories, and then it will give you what is the likelihood of these trajectories. And then you can use the generative model to do data analysis to calculate what would be the likelihood of the wrong data or another data, which is the time reverse. Again, if the system was in equilibrium, the generative model should tell you they have exactly the same likelihood because they are statistically completely equivalent. But if the system is out of equilibrium, this is a way by which you should detect that the likelihood of this trajectory is not what it should be. That's just, I'm just going to, there's other things you could do, but that's what I'm going to focus on right now. And I'll do that on a variant of the MIPS model, which is especially designed so that you actually can see from the trajectory that they are irreversible. Okay, so I didn't give credit to anyone because I don't know, probably this has been studied by someone, but I don't know who. So it's actually simply a quadratic potential, so it's a linear restoring force, which in the standard MIPS would lead you to no activity. But here is a twist that this is not what is actually being done. What's done is that the force here is simply something that is a Markov jump process between a value which is +1 or -1. So what this thing does is that you can think about it as motion into a simple well, a quadratic well that is time dependent, and it's either centered, on V0 or on minus V0. In this case, they were taken to be 1. Okay, and so what happened is that you're creating metastability in a bit of in the following sense, which is that for a while the system is trapped in this well, so it equates there, then this guy goes there, then he follows there, and then he equates there, and back and forth, right? And this is what's illustrated here. This is what G is doing. And you see that the trajectory tried to follow that guy. Here, I didn't write it, but there is a bit of noise that has been added to this. My apologies, it should be there. But you see that, the trajectory goes and try to follow. And if you look at this guy, you see that this is relaxation this way. This is why I choose that example, which means that if you were to look at it in reverse, you would see that something is going on. And when can you see the activity? Well, you can see the activity of the non-recurrent nature, not here, because this is essentially thermal, right? If this step is long enough, but here and here. Okay? And so, okay, so this is just an illustration, but you can calculate, so you can train a generative model to, in fact, give you this trajectory. And this example is really a baby problem. They just give you trajectory. So here we train a generative model to just take the trajectory of 10 times 2. This means 20 time slices with the discretization that we do. And then you can calculate, so then you can calculate the likelihood on a test set where you use 2 test sets. One test set is the actual trajectory, and the other test set are the time reverse trajectory. And you see that when you look at the distribution of likelihood on this test set, the one that is done on the reverse has a big tail of lower likelihood. Sorry? And at the same time, a chord as the same. So let me explain that also visually, which is, so if you color these pieces of trajectory by the difference of log likelihood between reading them forward or reading them in reverse, what you see is that essentially nothing is happening when they are in equilibrium. What you should see, nothing is happening when they are in equilibrium, but you have low likelihood each time there is a transition. Of course, again, this is a baby problem that is meant only for illustration, and we would like to scale this up, but it tells you exactly what you would want to see, namely that the signature of non-equilibrium is the transition. What's interesting here is that this was done just with trajectory data, without knowing the equation of motion, nor observing the G. This is only X that has been done. Okay, and you can do the same thing, which is that you can look for individual piece of trajectories. You can cross-correlate the likelihood of this trajectory and the likelihood of the time reverse. And you see that there is a block here, which is like, this plot are a bit misleading. It's like there's more point here. This block where they are correlated correspond to these bits. And it's also this. But this part here, where it goes below and where the time reverse are less likely, it corresponds to this tail, which also corresponds to these elements. Okay? So I don't have anything more exciting than this baby example today to show you, but the idea is that we're going to revisit MIPS and Vishek by doing this calculation that way. And that's all I had for you today. Again, thank you for your patience waiting for this talk. The conclusion in one sentence is to say generative AI, it is this dialogue, which is that statistical physics is very useful to generative AI, as Giulio explained, because it allows you or us to understand certain features of generative AI. But conversely, generative AI is actually very useful for statistical mechanics because it opens the door into doing calculation that not so long ago we would have deemed completely impossible. And that, you know, this is one example. Okay, thank you.
Thank you very much for this wonderful talk. Let's see if there are questions. Yes.
And the mic?
Yeah, probably.
Yeah, I mean Paris, I mean France.
Yeah, you have to do shadows. Sorry.
I had a question, maybe applies to all the systems, but in particular in the VTREC model case. Just in terms of the physics, I guess the special thing there is the long range order for a continuous order parameter in 2 dimensions, right? And you're saying that, you know, when you have a cluster, right, there's really no evidence of time reversal, right? For a large cluster unless the particle leaps.
Yes.
So how do you kind of reconcile those two things? Because if you have a kind of cluster with long range order in 2 dimensions, why not a deliberate, right?
That's too hard a question for me, I'm afraid, because I'm not an expert in, you know, in the VSHEC model. Maybe simply what I can say, one of the issue with the calculation that we do here is that they are some, at this stage, they've been done on systems that are not in any thermodynamic limit where you can start analyze the system like VSHEC. For MIPS, we have shown that you maybe can scale them up, but for VSHEC, we just took a system, I think there was a 64 particle, and that was that. What happened if you scale, when you scale this system up, is an interesting question, and it's an interesting question to know whether these tools can be used to do that, and that leads to this question of transfer learning, which is that at some point you would need somehow to have that your transformer architecture can be localized in the calculation, because you know you at some point, even for a neural network, if all particles talk to every particle in the system, there will be a problem. So whether having long range order would mean that it would break this, that's an interesting question, right? Let me say that maybe we know, because of the curse of dimensionality, that you can break these methods, right? You can construct adversarial examples that are not learnable, okay? And part, this is, again, this interplay, part of the big question, in fact, is to try to understand which systems are learnable and which systems are not, which essentially means, is there structure of the data or not? And statistical physics is actually a very good laboratory for this, these models to actually maybe try to, because these are systems where, as you know, and as you say, we have information. So maybe we can try to see if we go into things where you need to have long range order, where indeed you can't learn them anymore, etc. Very interesting question, but I don't have any better answer than that.
Okay. Question. Yes.
Really fascinating talk. In the last part, should I think of that as something like adding time delays so that you can get the full state? Like for a system with inertia, measuring positions isn't sufficient. I have to be either measure position.
That's right. So that's okay. That's right. So I mean, if you look at this system, maybe I can elaborate a little bit on this, right? If you look at a system like this, if you were just to look at one time slice, so that's the statistical information that you have on this time slice, and clearly, you know, you can design an equivalent system that has this like distribution, right? So clearly, if you want to measure something which has to do with, you know, the non-equivalent nature, either you need to use information about the dynamics that you don't have, or you need to use information about trajectory. So that's the route that we took here, is to say, well, if I just look at this, I have that, but we don't want to learn this. We want to learn the joint probability of time slices, 20 time slices around here, and that gives you some information about the non-equivalent nature. Now, why 20, why t equal 2, all of this is something that is, you know, again, is system dependent, right? And again, we could probably break that with systems that have, you know, long correlation time. Here, there's not the long, the correlation time is gamma, whatever, you know, the parameter that was used here, the typical time here. Right? But that's really the idea. Like, so there's no, if you just look at snapshot, you can't do it. So again, even this system, which is in one dimension, what you observe, it becomes high dimensional, right? The learning of the score here is a 20-dimensional function, since we need to learn a score to generate trajectory, which have 20 discrete time.
Okay. Final question? Yes. You deserve one.
Yeah, so it's on this last part. So I wonder whether actually there is not the inherent difficulty to scale up what you're doing here, in the sense that, I mean, this system learned the score and they learn this high dimensional function, but not everywhere in the configuration space, but only on typical configuration. So this means that the time reverse trajectory, it has a low probability, so if it's a typical, it's in a region of the space that actually during the learning have never been treated. And so there probably the score is very, very wrong. So in low dimension is fine, but in high dimension, I think there is a problem in the sense, even when you do supervised learning, you don't learn the function everywhere, you just learn it on the manifold. So
in fact, what it's a good point. What we did is slightly different. I mean, I presented this because it was easier. What you can do is that you can learn a score. You can learn two generative models. One that generates, trajectory that are forward, and one that generates trajectory that are backward. And then once you have done this, it's easier to compare. Okay, but it points out to another, advantage here of these methods in the context of statistical physics, which is that this problem, which is that when you learn on data, it's not completely clear how much they generalize outside, is everywhere in machine learning. I mentioned GenCast, which is the forecaster of Google, right? So it's weather forecaster that has been trained on the reanalyzed data from ECMWF, European Center for Weather Forecast. They have 40 years of data. Once you train their generative model, you can now use it to generate statistics of events that have a recurrence time which is 1,000 years. And they do it. And so you can ask yourself, that's the question that you're asking, is this reliable? Because at the end of the day, I had 40 years of data. I've never seen any such event. And, can you extrapolate there? So these are, very interesting questions. What is interesting for models that you can simulate, and this is not for experiment, is that then you can generate the data on the fly. So this is online learning. So you can, in principle, use this information in concert. That's another talk, but you can use this information to do important sampling Monte Carlo, where you slowly learn how to push the system in regions that are rare, and then you learn the score there, because it's a feedback loop. So if you know how to push system there, then you can learn the score there, and then you can go further.